So now let's go to a second point of this chapter 9, looking at the non-renewable energy sources. What are they, how do they form, and looking at some specificity regarding those energy sources. Most of those energy sources, non-renewable energy sources, tend to be fossil fuels, but not all of them. You will see that in just a bit. These fossil fuels are coming from organisms, very small organisms, organic matter that has decomposed over a long geologic period of time. In general, it's taking about hundreds of millions of years for this fossil fuel to be formed. Nothing is at human scale. That's why we don't speak about renewable energy, because it's outside of the human scale. It's taking way too long to be renewed. In general, those fossil fuels tend to be three main energy sources, not only, but we have derivative from that, three ones, which are in fact coal, oil, also called petroleum, and natural gas. All of the three fossil fuels are coming from organic matter, organisms that have died, accumulated, decayed over time, fossilized in fact. And the majority of these organisms tend to be photosynthetic, but not only. But all of them tend to be very small organisms, not just like in this picture. They tend to not be dinosaurs, and don't think that dinosaurs melted to give you oil and possibly coal, and that the fat of the dinosaurs give you natural gas. It's not the case. Most of those fossil fuels are coming from very, very small organisms that have accumulated over time. Why that? Because in fact, those small organisms tend to have high hydrogen carbon content to specific chemical element that in fact, when they bond together, have a very high energy content. And so the separation of this bond is in fact releasing a lot of energy, and we do the separation of this bond when we are burning them. And so that's why those small organisms tend to be very effective in producing fossil fuel, but over, again, a very long period of time. We have two sites of formation for this fossil fuel. First, we have oil or petroleum and natural gas that will be formed only in marine environment, because in fact those fossil fuels come from the decaying of marine phytoplanktons and zooplanktons. Phytoplanktons being the equivalent of being algae in the marine environment, and zooplanktons being very small crustaceous-like animal that will feed on phytoplanktons, on the algae. On the land, we have also fossilization of organic material that will provide us coal. And in fact, this organic material is mainly plants. Plants will be decaying, accumulating on land, and will produce coal. All of those fossil fuels tend to have the same kind of formation. They all come from accumulation of organic material that will be decomposed without oxygen or very little contact to air. And in fact, that's what we call an anaerobic decomposition, when it's happening without oxygen. And it happens in aquatic environments. So if it's in land, it will happen in deep lakes or in swamp. If it's on the ocean, usually it's within shallow seas. And you can see this illustrated in this figure. On the left side, that's the example for the coal with the swamp, and on the right side, that's the example for petroleum and for natural gas. We have on the left for coal the accumulation of plants on the swamp. Meanwhile, in the shallow sea, you have accumulation of planktons, either phytoplanktons, the algae, and zooplanktons, the carnivorous planktons that are just accumulated at the bottom of the sea. Then when it's happening, when they accumulate, they're following the same process, which is in fact accumulation of this organic matter tend to be, in general, small. If they are not small, they will be cut apart into small pieces and start decaying. And this have they will start accumulated over time. With the accumulation, you start having a burial. They get buried, and as they go buried, you're increasing in fact the temperature and the pressure. By increasing the temperature and the pressure, you're changing the physical shape of those organic matter that will in fact do some rebounding. The density also will increase, and coal will tend to stay in solid phase. Meanwhile, with a higher pressure and temperature, the organic matter in the sea will tend to liquefy to produce us the oil or petroleum, and even a little part will in fact turn into the gas phase to provide us natural gas. We'll talk about this in just a bit. At this point, let's focus on coal. Coal is formed again on land only. This usually form either in deep lake or in swamps. And so at these sites you have accumulation of vegetation that's usually in the surrounding. These dead plants will accumulate at the bottom part. You will have sediments covering it and kind of trapping this layer of organic matter that will be buried and buried and buried, and so temperature will increase, pressure will increase, and this organic matter that contains a lot of hydrogen and carbon will in fact densify, and the bonding will in fact increase, meaning that you will in fact accumulate a higher energy content than it was in originally. And that happened over millions of years. That's taking a lot of time to happen. So when you go to a site like that, you may have the chance to see coal at different stage. If you're coming at the point that it's just starting accumulated and sedimented, you will have a very low energy content coal. In the contrast, if you're going to a site where it has been accumulated and buried over millions of years, your coal will be very enriched in energy. So you can expect to have what we call different grades of coal. The worst one is peat, which in fact is not usable for energy in itself. The first type of coal that can be used to produce energy is in fact called lignite, the first stage of decomposition and formation of coal. As we can see from the graph right here, lignite tend to be high energy content, but the smallest one in comparison to the other one. If you want a higher energy content coal, you'll have to give more time to obtain what we call the subbituminous. This has a higher energy content. You can see it's becoming darker, meaning that in fact the carbon and hydrogen tend to be accumulating more and more in this rock. And then if you give even more time, you're going into bituminous coal, and the best one, the one that has the most energy content for its size, is in fact the anthracite. The anthracite, as you can see, doesn't have that much energy more than bituminous, but in fact it's a pure source of energy in comparison to the other one. The other one usually you still have to clean it and add some trace of other sediments. So again, the longest you give for the formation of the coal, the highest the energy you will get. This energy again is obtained by burning coal. So usually you're burning, for example, water to make turning a turbine that will turn a generator and producing electricity. And when you do the burning, you're breaking down the bonds of hydrogen and carbon, which release in fact the energy that will be used for the steaming. In terms of the reserve, mostly the main reserve that we found in the world of coal is found in North America, between the US and Canada. As we can see from the map here, we have about a third found there. Then another third is found mostly in Asia and Australia, as we can see here with China and Australia, the blue, it's about a third, and almost another third found in Northern Eurasia, mostly Russia at this point, a bit in Germany and Western Europe and in Eastern Europe, but mostly Asia. That's the main one, mostly Russia. As we can see, Africa tends to have a little reserve, and South America is not really rich of coal. That's just based on geological history of all of this region of the world. at this point, I let you watch the movie about coal that you can find with the link on YouTube. It's also available directly from the webpage on CAT courses of this chapter 9 on conventional energy resources. So pause this video, and whenever you're ready, come back to this one and keep playing it. So now we're done with coal. Let's go for the next fossil fuel, which is in fact petroleum. So very similarly to what we saw with coal, petroleum form also with the accumulation of organic matter at the bottom part of a body, water, which is at the water body, which is at this point a shallow sea. So usually not so far from the coast in itself. And these small organisms, mostly phytoplanktons, algae, and animals such as zooplanktons, very small size, will accumulate and be buried over time, millions of years again. And with this burial, an increase of temperature and pressure will consolidate, densify this material, and usually those temperature and pressure are higher, and we start in fact liquefaction of this material, petroleum. And so the main reserves at this point are different from those from coal. If we look at a map, mostly we see that the majority of petroleum is found in the Middle East. So with Saudi Arabia, Iran, Iraq, Kuwait, United Arab Emirates, that we can see from the list, that represent more than 50% of the actual reserve of petroleum. But interestingly also, if we look at the data, about 90% of the world petroleum reserves is controlled by only 3 countries. The major ones are, those 3 countries are Saudi Arabia, Venezuela, and Canada. You may have heard especially about Saudi Arabia and Venezuela, and might be a little surprise to hear about Canada, but they also have a lot of petroleum. And then after you see other small countries, other smaller reserves are found in other countries such as Russia, Qatar, and you can see that China and US tend to be having some petroleum, but not that much. In fact, the US tends to have a very thick petroleum available, and in the future they expect to sell this one more and more as possible reserve of petroleum will go down. So again, very quick introduction about that. So I let you check now this movie on oil, available on Facebook via the link, or that's also a video that you can find on the CAT course webpage of this chapter 9. Whenever you're ready to come back, just play it back and we'll keep on working with natural gas. Okay, so I suppose now you've watched the movie on oil. Let's turn to natural gas, which in fact tend to be formed mostly with petroleum. A little, there is natural gas being formed also with coal, but that's a minority. The majority of natural gas tend to form during the burial of petroleum, when the increase of heat tend to be that much that you have liquefaction of your oil, and in fact you have some evaporation of this petroleum going into a gas phase. And so that's again another illustration showing what we saw in the previous slide, where you have a small organism that will accumulate at the bottom part and accumulation of other sediments over it. You have those sediments being inside of what we call a porous sedimentary rocks, like almost think about what we saw for groundwater with a lot of space in between the different grains, making available for this petroleum to accumulate over time once it will liquefy, as we can see right here. You have accumulation of petroleum and in fact emanation of some gas, that's a natural gas. So again, we can see that sometime with the formation of coal, but in general natural gas is mostly found within the formation of oil at this point. This is the highest energy content fossil fuel. It's one of, in some way, if we can say it, it's purer than coal and petroleum in terms of emission of CO2. That's why over the last decades we've turned more and more to natural gas for the production of electricity. As we saw during one of our exercises, in fact, natural gas tend to be about 34-35% of the electric production of the US, when coal tend to lower down to about 30%. At this point, again, make a pause on this video, watch this movie available either from YouTube or also on the CAD course webpage of this chapter 9 lecture, and whenever you're ready, come back and play it back. Finally, the last conventional energy resource, the last non-renewable energy resource, is in fact nuclear energy. And nuclear energy, unlike the other energy sources that we just saw, does not emit directly CO2. Okay, that's one difference. That's also why a lot of countries turn to this energy that is very efficient. A lot of countries, as we'll see in a bit, turned to that energy about 30 years ago. Two types of production of a nuclear reaction can be done to provide energy as heat. The idea is to have a nuclear reaction that will produce heat. You're warming up liquid, usually water, to make turning turbine that will start a generator that will produce electricity. The first one is what we call fission. That's the one that is used currently in all the nuclear power plants in the world. And the way it works is just having a radioactive element that is within a reactor, and you bombard this element with a lot of neutrons. What happens is these elements becoming unstable, splitting into different less radioactive elements, still radioactive anyway, and releasing energy at the side. And this energy is released as heat, being used to warm up, to boil water, for example, or to boil any liquid used for the production of electricity in general. The other reaction that has been looked and researched a lot is in fact what's happening right now in the sun and in any stars in the universe. It's what we call fusion. Now, fusion is when you have two elements of hydrogen that will combine together and to create a heavier element called an helium at this point. During this combination of hydrogen, which is very unstable and very risky, the formation of helium will release very, very high content energy. At this point, this is still under research, with the idea of possibly reaching the nuclear fusion within the next 20-30 years, possibly. For now at least, we are just nuclear power plants only using fission, not fusion. No, there is no nuclear power plants using fusion. It's still too unstable. We haven't been yet figuring them out. Possibly by 2040, the first power plant might be created, but it's still with a lot of uncertainty, and especially because nuclear energy has been less and less promoted in general by most of the countries on the world due to the risk linked to and the different accidents that happened because of nuclear power plants. Regarding the reserve of nuclear energy resources, we mostly found them in Australia, which is a country with the most natural uranium reserve. Uranium is the radioactive element that is mostly used for fission reaction. As we can see, it's more than a third of all the reserve that we can find. It's about a third of all the reserve that we can find in the world. Then after, uranium is found in other countries, but in less quantity. And so it's interesting that if we do the calculation, about 15 different countries almost have the overall reserve of uranium, with again Australia accounting for a third of it. Even though the US, which is right here, standing number 9 in terms of reserve of the world, the US tend to have the highest production of nuclear energy in the world, even though it's not the main energy resource being used in the US. We'll see that in just a bit with a graph to come. So if we look at the production of nuclear energy by country, we can see exactly that the US are the first country in terms of nuclear energy production, followed by France, Japan, China, Russia, Korea, India, and Canada, and so on. And so this potential high energy production from nuclear energy is in fact coming from the fact that a lot of reactors are found in the US. The more reactors you have in a country, the more production of energy you're making. However, it's not because the US is a main producer of nuclear energy that nuclear energy is the first production in the US of electricity. In fact, the US use natural gas much more and coal much more to produce electricity than nuclear energy. And so if we look at the contribution of nuclear energy within the electricity production for each country, at this point there is a change. France is making about 70% of its energy from nuclear energy. It's the highest, it's a country with the largest contribution of electricity production from nuclear energy. Then after followed by Ukraine, Slovakia, Hungary, etc. And if we look, the US is right here in the middle of the table. So quickly, just to remember, the US are the world's largest producer of nuclear energy. However, producing about 30% of all nuclear energy in the world, to mention, but only counting for 20% of the country's full energy production. Only, okay, so it's not a major one. While in fact France, which is the second producer in the world, makes about 71% of its energy coming from nuclear energy. So why nuclear energy is so good, or why is it interesting? Well, if we look at this graph, what we can see is if we would compare how much volume we need of the energy resource to produce the same amount of electricity, we'll see that for coal, we would need about 250 trains, with each train having 100 wagons, to produce the equivalent of the same amount of energy of petroleum that would have 10 oil tankers. Or if you want, you have, I forgot to mention, the weight right here, which would be the same equivalent energy produced by 7 cargo ships containing gas. Okay, there's still a lot of stuff, still a lot of volume to produce energy. What about nuclear energy? Only one wagon of train of uranium. You see the main difference. It's very small. You have, again, another equivalent at this point. For example, a uranium fuel pellet, which is the size of a coin, is the equivalent of 3 barrels of oil, or 1 ton of coal, or a big tank of natural gas. That means that, nuclear energy tends to be very efficient just for a small volume. However, uranium is hardly found in the world, and so just making one pellet of uranium is also very it's very costly because of its hard extraction. Okay, so at this point, again for the last time, I'll let you watch this video on nuclear energy. And whenever you're ready, just click on the last video that is available from chapter 9 of this CAD course webpage. Okay, see you in a bit.